This lecture is going to focus on differentiation using logarithms and the natural exponent. We really could have done this earlier in the semester. These are just standard differentiation laws. But we're going to do it here because the next thing we're going to pursue is logarithmic differentiation. So, presumably it'll be fresher on your mind at this point. Essentially, we have for the function e to the x, so this is a exponential function. The power is x, the base is e. E is just a number, 2.718, whatever. Just think of it as like pi. Pi is a little bigger than 3. The exponent, the natural exponent, is a little less than 3. Roughly speaking, it's 3 to the power of x. This function is unique, though, in the sense that if you take the derivative of this function, you get the function back. So the derivative of e to the x is e to the x, which is a rather interesting property. Going along with this is the derivative of the natural logarithm. So this is the natural logarithm is the logarithm to the base e. The derivative of the natural logarithm is 1 to the x. So these are your basic rules here. These are included in my crib sheet. So these are standard problems, and we're just going to work out standard differentiation problems involving these functions, and of course there'll be a lot of chain rule and so forth and so on. But we'll just work through these. Okay, so here's our first example. Let our function f of x equal x times log x, and we want to find the derivative. So it's going to follow in exactly the same way that we do everything. Again, you don't have to write this down, but you should always think about what the function is. Is there any basic simplification that needs to be done? This step will be key when we do logarithmic differentiation in the next section. So it's a good step always to include. The key feature here is that the domain has to be positive numbers. Whatever goes into the logarithmic function, whatever goes into this box, has to be a positive. That's just the definition of log. Now, I'm not going to go over all the properties of logs and all the definitions of it. You did this presumably in pre-calculus. If you want to review, that's fine. We're just going to be using the differentiation rules essentially. In terms of differentiation, we just follow the standard format. I mean, there's nothing really remarkable about any of this. By definition, fx is what comes out when you apply the differential operator to the function f. So this is by definition. We simply replace f of x by its rule, right? And just by definition, we're at this step. Now again, when you look at this, what rule do you want to use? Again, you can pause the video and try this. It's just the basic rules. There's nothing particularly fancy here. So pause and give it a shot, and then when you're ready, start up again. Okay, so at this point, if you look at this, only one rule applies here, right? It has to be the product rule. You simply do not have any choice in how you're handling this problem. So if this is the product rule, you would just take first times derivative second plus second times derivative first, and that's it. Now, there's no problem dealing with this term, so there's no sense to get creative about this. I guess I did this term first. That's just the derivative of the log function is 1 over x. And of course, the other term, x is x to the first power, derivative of x is 1. And that's about it. It cleans up. Notice we're defined only for x positive, so this term makes sense. This simplifies to 1. And that's all there is to this. Again, it's a fairly straightforward problem. Again, there's nothing wrong with that. But again, what I want you to understand is you don't have a lot of flexibility with how you apply the rules. It's just follow the rules. Get comfortable with that. Here's the next example. So now the new feature is we have log, but it's not just x in here, right? It's 2x in here. And again, we just simply want to determine the derivative. Again, if you want to give this a shot, pause the video and give it a shot, and then start the video up again and compare. Okay, again, I'm going to look at, in my preliminary step, consider the domain of the function. And again, I have x greater than 0, positive numbers. And the reason is log is only defined, whatever goes in here has to be a positive number. In our present case, you see, what goes in there is 2x. So 2x goes in the box, and it has to be a positive number, which means x has to be a positive number. And that's how you derive this. Again, I'm not suggesting you necessarily should write this all down, but it should cross your mind. You should certainly think about it. So differentiation, again, it's going to follow the exact standard template. You just cut and paste the previous slides. By definition, if f goes in, fx comes out of the differential operator. And by definition, I replace fx, right, by its definition, log 2x. Now again, when we look at this, we can't just use the differentiation rule, derivative of log x is 1 over x, because this is not the log of x, it's the log of 2x. And again, close is not good enough. It has to be exactly as the rules require, or you can't use it. So the only rule that applies to this, the only possibility would be the chain rule. So we have to try the chain rule here. So let's take this out and look at it as a chain rule problem. So again, we'll just set it up in exactly the chain rule template, right? We want it to be a function h equals f of g in my notation. You can call it whatever you want. So my function h is going to be log 2x, and we're going to define the function hx. So it's in the same standard formation, same standard template. So if I'm using the chain rule, I'm going to identify functions f and g such that h equals f of g, right? So we need to find these functions. And once more, we'll just follow the standard template. H equals f of g. G of x is going to be the x stuff. So we have g of x equals to 2x. Y equals g of x by using the composition of functions. So this term here is going to be y, and that's going to specify f of y. So we have identified the function f and g. Again, f is a function of y, g is a function of x. And once more, it's never a bad idea to check that what you're doing is correct, right? So we simply plug in the g of x here, f of y equals log of y. Y is again a placeholder. Whatever goes in here gets placed into here. What goes in that box is 2x, so f of 2x equals log of 2x, and we see that that's exactly what we want. So once we have the function f and g, we need, in order to use the chain rule, we need their derivatives. Again, f is a function of y, so we need its derivative fy. G is a function of x, so we need its derivative gx. And this will just be the same thing we've done in the past. F of y is log y, so we need its derivative. G of x, and we need gx. So you don't have to make a big deal. Well, you can do these in your head, of course. The derivative of log y is 1 over y. The derivative of 2x is, of course, 2. But if you were to put in all the rules, you take out the 2. X is really x to the first power. But again, what we're looking for is essentially just this table, right? You don't have to write it all down. We're looking for this table. Just f of y is log y, take its derivative. G of x is 2x, take its derivative. Notice I'm not putting in all the steps with the chain rule anymore. We've already done it a lot. You have to have composition of functions. The chain rule is just simply this. Again, it doesn't take that many lines to do it correctly and to be careful about it. Remember, I'm not against shortcuts, but the more lines you leave out, the higher the probability you're going to make an algebra mistake. And that's going to cost points on exams. So we'll just plug in the data right here. G of x, gx is 2. I plug that in there. G of x is 2x. We just plug that in here. Fy is 1 over y. So again, y is a placeholder, right? The y is just a box. And what goes in that box is 2x. So once we place that in the box, now we know what fy of 2x is, and we put that in here. And now it's just algebra. We can just clean up and get 1 over x. The 2's, of course, cancel. And so that's our derivative. Now we'll just take this in a modular fashion and go back and substitute it into our original problem. So I suggest fold the paper in half. Do these kind of calculations on the right side of the paper and just substitute it in on the left. I think that's a very effective strategy. So this is where we left off, and presumably we included all our work on the right side of the page. I will just substitute in our answer, and that's it. And that's the answer here. Now again, this did just come out 1 over x, but again, it's just coincidentally that the 2's and so forth canceled. All right, now let's look at another problem. And again, let's pause the video and give this a shot and see how it goes. Again, when you're ready, start up and compare. Okay, so let's take a look at it. I like to take a look at the function and make sure we know what we're talking about. Again, I wouldn't necessarily waste time on this on an exam, but it's just a good technique to follow. Log x is here, so log is only defined when whatever goes in the argument is positive. And that's pretty much what we have for the function. There's no real simplification we can do with the rule here. Again, the argument has to be positive. That's all we have from this. Again, this is just a template standard form. F goes in, fx comes out. By definition, this is what we have. By definition of the rule of fx, we go to this line. Now, when you look at this, there's no other rule you can do here except the chain rule. It's the only possible rule that applies. So if it's going to be the chain rule, we have to, again, find f and g such that h equals f of g, take their derivatives, and so forth. So again, the strategy is already planned out for us, right? So on the side of the page, let's look to do this. This is what we're interested in. If it's a chain rule, it has to have, in my notation, we're saying h equals f of g. So we have this. We're looking for the function hx. Our function h then is this argument, right? So to put it in a standard chain rule format, this is what we have. This is our given function, and we want to find the derivative. So again, if we're using chain rule without any thought, without making work or worrying about it, we need the functions f and g such that h equals f of g. And again, you can just do this. You don't have to write this out, but this is the thought process. H equals f of g. This is what the rule is. G of x is going to be the x stuff here. Again, you don't have any choice in how you're going to do this. So g of x is going to be the log of x. And by the chain rule, by composition of functions, I mean, y equals g of x. So this is y, right? And so my function of y, right, that's y. My function of y is going to be y to the 4. And g of x is going to be log x. So this just checks that we've selected the functions correctly. G of x equals log x. F of y is y4. Again, y is a placeholder. Whatever goes in that box gets placed on the left and the right. And we see that we did, in fact, make the correct choice. We did recover the function. Again, you want to check this to make sure you didn't make any dumb errors. You didn't do some algebra wrong or something happened. You don't need to do this, write it all down. You don't need to take 10 minutes. But again, it's a good technique. It's a good form to check these things. Now, once we, of course, have f and g, in order to use the chain rule, we need the derivative of f and we need the derivative of g. F of y is y4. Again, it is calculus of a single variable. It's just in this case, the variable is y. G of x is log x. We need the derivative, gx. And we'll just plug in and take the derivatives. F of y is y4. Derivative of y to the 4 is 4y cubed. Again, I don't know if you need to write these. At this point, these are pretty basic. The derivative, gx is log x. Derivative of log x is 1 over x. So really what I'm looking for here is just this table. Right? We just need this table. We have h, we have this table, we have the chain rule, and we'll just plug the data in and we're good to go. So gx is going to be 1 over x. G is going to be, right, log x. Fy is 4y cubed, right? And whatever y is just a placeholder. Again, whatever goes in this box gets placed over here. Log x goes in the box on the left, log x goes in the box on the right, and we can just substitute that directly back in and simplify as needed. I mean, this is how I simplified it. You could do whatever. So we have this derivative, and now we'll just take this and plug it back into our original problem, and that's it. Okay, so that's it, and we're done there. So again, these are fairly straightforward, I hope, straightforward application of the chain rule. Of course, the rule, the derivative of log x and the derivative of e to x are new, but the way we're doing the problems is exactly the same. Now, this problem is a step harder. You can see it's a much more involved. It's a much more involved function rule. But again, it should follow the same way. If you have good technique, this should not be a big deal. So I'm going to pause the video here and give it a shot and see how you go. Just be careful. Just follow the steps, follow the process. Again, don't fight harder, fight smarter. So good luck with that. Start the tape up again in a minute after you give it a try, and we'll work through this together. Okay, good luck. Okay, so let's come back. What we have is the function is the log of x squared. And again, what does this mean? I don't know. It's just a homework problem, right? It doesn't make any difference. So how did I figure out the domain here? Well, again, let's look at this more carefully. Again, for an exam, of course, I wouldn't take the time to figure this out. But, I mean, you should understand how these things work. Log of m, whatever in the argument has to be positive, right? In our case, this is log x squared, has to be positive. So what x makes log x squared positive? Log x squared is positive as long as x squared is greater than 1. Again, these are just properties of logarithm. Again, you should know this from pre-calculus. If you're not up to speed on this, you can review or, don't panic about it. This is not the kind of thing I'm going to push on exams or anything like that. But other people in other classes have different, requirements or what they want. And so it's not bad to review this stuff. So log of the argument is greater than 0 when this is greater than 1, just from the graph of the logarithm. So we have this polynomial greater than 1, or this function. And how would I generally know whether something is greater than 0? Well, whenever you're talking about positive or negative signs, you should remember what tool do you have in your toolbox in general? The sign intermediate value property. So using the sign intermediate value property on this function would tell you that x has to be either less than 1 or greater than 1. Again, it's just good experience. It's a good discipline to think about these things. What tool do you have in your box when you're looking for something being positive or negative? The sign intermediate value property. So again, you have a finite number of tools in your toolbox. Learn to use them, right? It's not being spinning your wheels. Fight smarter, not harder. So that's how we get the domain here. Of course, it's a one variable problem. You could just go to graphing calculator and plot it, but still, I mean, you should be able, you should know this in general. So now we're just going to follow the general differentiation technique. Again, standard f goes in, fx comes out when we apply the differential operator. By definition, the function rule is given by f of x equals log x squared. We plug that in. And now again, when you look at this, what rule on the crib sheet applies here? You don't have any choice in the matter. It has to be the chain rule. You don't have a choice in the matter. It has to be the chain rule. So again, if you didn't get that, take a moment, pause the video and try it, but it'll be the chain rule, and we'll come back and do it again, and you can compare your work. Okay, for the chain rule, I'm going to set it up in the standard template. Again, you only have so many tools in your toolbox. I'm going to take my function h to be this, and I want to find its derivative, right? So h, if I'm going to take h equals f of g, I need to pick my functions f and g. And in fact, you have some flexibility here. You could have taken gx to be x squared, and then f to be log y, but I'm just going to take gx to be, in this case, log x squared. Again, you could have taken it to be just x squared. You're going to do the chain rule again, so you're just either going to do it on the function f or the function g. So that's g. So y equals g of x in the notation of composition of functions. So this is going to be log of y, and that determines my function of the variable y. Again, it is functions of a single variable, but the variables are different. So once I have the functions f and g, I need their derivative. But again, let me just check quickly to see that I've applied everything correctly. Right? I've substituted in gx. I'm going to check f of gx is the correct form, and you can see that it in fact works out. So I'm confident that my choice is correct. I have to go forward with it, but I'm confident. So I have f and g, and now I need their derivatives. Right? If I'm going to apply the chain rule, I need fy and gx. So f of y is log y, and I'll try to find its derivative in a moment. And I need gx. G of x is log x squared, so I'll need its derivative in a moment. Just do the pieces that's easy first, right? F of y is, I substitute in the rule, and then the derivative of log y is 1 over y, so this was standard. But notice when I come to this side, I don't have a rule for the derivative of log x squared. I know you can bring the power down and so forth and so on, but let's just do it without getting too fancy. If I'm going to look for a rule to apply here, what rule should I look for? I'm going to look for the chain rule again. So let's just break this off, and this is what we want, right? This is my function log x squared, and I want to find its derivative. So if I'm going to use the chain rule here, and again, you notice I'm not putting in the steps as often as possible anymore. You should be a little more comfortable with moving this along at this point. I'll take the outside function to be log y and the inside function to be x squared, right? And if I check, it works. And if I take their derivatives, right, for the chain rule, I need their derivatives. F of y is log y. I take its derivative, 1 over y. G of x equals x squared. I take its derivative, and it's 2x. So here's my table of data, and I just plug it into the chain rule and simplify it, and it just comes out to be 2 over x. Again, you should be able to do this in really 6, 7 lines. It should be relatively quick. This should not be a 20-minute exercise. If you're struggling at that level, you need to look at the notes, try more problems, and if you need help, you need to get help. So again, fight smarter, not harder. If you're struggling on this, it's a sign. So this should be pretty straightforward. Now I'm going to take this and just go back to where we left off, right? So I'd work on the right side of the page. I'll just take this and plug back in here and get 2 over x. So again, there's a chain rule and a chain rule, or I know you could use the power and bring the 2 down, whatever. It's fine. Chain rule and a chain rule, it's not that shouldn't be that difficult. So once I have the derivatives here, I'll apply the chain rule on this function, right? Here's my data, and here's the chain rule. So I'll plug in gx, I'll plug in g, I'll plug in, well, fy is 1 over y, so I'll just plug the data in there. And then simplify any way you feel you need to here, and that's it. So I'll go back now again to the original problem, right? And this is where we left off the original problem, and I'll just plug that in. Again, what I want you to see is you just keep breaking things down on the right side of the page and plugging them back in. Be organized, and no single problem should be that difficult. You're just using the basic differentiation rules. If you're struggling and using a lot of the rules, then maybe simplify things, maybe improve your technique, because every single step should be pretty straightforward. There's not a lot of variety in how you can approach these problems. Finally, let's look at this one. Again, the difference is this isn't e to the x, it's e to the x squared. So you can't just use the derivative of e to the x as e to the x here. This is necessarily going to be a chain rule problem, but let's cross that bridge when we get there. So I'm just looking at the definition. There's no easy simplification or obvious simplification here. It's fine for all real numbers. The range is all real numbers. Again, you can give this a shot. Pause the tape and try it, and then come back and we'll see. Good luck with that. Hold on. Okay, coming back again, standard technique. The function f goes in, the function fx comes out. I'm replacing fx with its rule by definition, fx equals e to the x squared. And again, you can see I can't just say the derivative of e to the x equals e to the x, because it's e to the x squared. So the only rule that can apply here is the chain rule. That's the only possibility you have. If you have the chain rule, you have to come up with the functions f and g such that h equals f and g, so forth. So again, if you haven't done that, pause the video and give it a try, and I'll do that in a moment. All right, so look at this term. Okay, so I'm going to use the chain rule. This is my function h equals e to the x squared. I want its derivative, and I know that I need the functions f and g. So I'm going to take g of x to be x squared, and I'm going to take f of y to be e to the y, and you can see it all checks out here. Again, I'm not going to put in as many steps going forward at this point. We've done a lot of this at this point, and you should be comfortable with it. Now, once I have f and g, I can take their derivatives. And you see that it's not really that difficult. Like I said, every single step should be straightforward if you're setting it up correctly. Derivative of e to the y is e to the y, and the derivative of x squared is just 2x. Now I'll take this data and plug it into the chain rule. All right, so here's all my data. And I'm going to just simply plug everything back into the chain rule. And I get the derivative of e to the x squared is 2x e to the x squared. So again, this is new. You can still be making mistakes with this, but you really should be getting up to speed with the chain rule and everything at this point. So I'm going to go back to my original problem, presumably just work this out on the right side of the page. That's my suggestion. And we'll just plug it back here, and that's it. And we're done. Okay, so that's all we have to say with the problems for here. There's some, and next we'll move on to logarithmic differentiation.